Welcome to another informative series brought to you by Ortruo. In one of our last series, we look at the electrical grid. The way different generating sites are interconnected in parallel was looked at. That is the conditions that must be met before synchronization. Finally, we look at how synchronization are done using 3 dead lamp method. In today's series, we will be looking at the secondary transmission lines. So without any further ado, let's get started. The importance of electrical energy cannot be overemphasized. That is because electrical energy has grown immensely over 2 centuries, which is because of the flexibility it provides for its users. The variety of its uses has led its demand to increase monotonously. This means, more users are using electricity ever than before. And because the consumer end is always far from the generation station, the electrical current that is interconnected at a grid will further be transferred by another section of transmission lines at high voltage to a substation, which is a little bit more closer to the consumer end.
The reason why the voltage is stepped so high is to increase efficiency. Because, as electricity is transmitted over long distances, there are inherent energy losses along the way. So, high voltage transmission minimizes the amount of power lost as electricity flows from one location to another. These can be proven mathematically using these mathematical equations here. P is equal to I multiplied by V. And when P is the electrical power, I is the current, and V is the voltage. So it can be said that electrical power is equal to electrical current multiplied by voltage. And because there will be a voltage drop from one end of the wire, this can further be proven using Ohm's law. That is, voltage is equal to current multiplied by resistance. So when we substitute for voltage here, then electrical power will be the square root of current multiplied by the resistance.
So we can say that in order to reduce the resistance of the conductor, there is a need to increase its cross-sectional areas or use more conductive materials. But going by that route will not be cost-effective, which is because the transmission line's termination is in several meters. So using that approach is not practically attainable in terms of cost. Also, an increase in the cable size also leads to more weight. So the best possible approach is to reduce the current by more than half. And the best way to achieve the required power needed at the receiving end is to increase the sending end voltage. That is, the higher the voltage, the lower the current. And the lower the current, the lower the resistance losses in the conductors. So when resistance losses are low, energy losses are also low in the same vein too.
We all know that the consumer end is several kilometers away from the generating station, hence the reason why the voltage is stepped so high. To further prove it practically, let's connect these electrical loads here directly to the main there using a wire that has small cross-sectional areas. We would see that after some time, the electrical cable will begin to heat up as the current begins to flow. The heating up of the cable is as a result of more current flowing through the wire at that point in time, and also as a result of the length of the wire. If we should break down the termination into segments in such a way that the step-up transformer is connected to the main, while the secondary side of the transformer is terminated to the primary side of the next transformer. In our case here, the second transformer steps down the voltage to the rating of the voltage at the main. Now, current flows within the cable without generating heat even when the same cross-sectional area of cables is used, and the load remains constant. It is for this reason that electrical engineers usually consider some factors such as the power being transmitted and the distance required for transmission when determining the optimal transmission voltage that will suit the line.
There is also an economic benefit associated with high voltage transmission. The lower current that accompanies high-voltage transmission reduces resistance in the conductors as electricity flows along the cables. This means that thin, lightweight wires can be used in long-distance transmission. As a result, transmission towers do not need to be engineered to support the weight of heavier wires that would be associated with high-current lines. These considerations make high-voltage transmission over long distances an economical solution. And it is on this note that transmission lines can be categorized into three, which are short transmission lines, medium transmission lines, and long transmission lines.
A short transmission line is a transmission line that has an effective length that is less than 80 kilometers, and with a voltage rating that is less than 69 kilovolts.
Unlike medium transmission lines and long transmission lines, which have a longer span of line length when compared with short transmission lines. However, in short transmission lines here, the line charging current is negligible, and hence the shunt capacitance can be ignored.
The short transmission line can now be represented with a simple circuit diagram here, where the first impedance is the resistance, which is denoted R, and followed closely by the inductance, which is denoted XL. On the one side here is the sending end voltage, which is denoted Vs, and on the other side is the receiving end voltage, which is denoted VR. The arrow here represents the direction of the current, and here is the load that is connected to the circuit.
Now, we can use this circuit diagram to solve this problem here. A short three-phase transmission line with an impedance of 5.4 ohms and 7.3 reactance respectively per phase. The line has a sending and receiving end voltage of 66 kV and 58 kV respectively at a power factor of 0.9 lagging. Now, let's determine the power output and the sending end power factor.
Those parameters here are in line with the rating, so there is a need to convert them to phase voltage. For the sending end voltage, 66 kV divided by √3 will equal to 38,105 volts, while for the receiving end voltage, 58 kV divided by √3 will equal to 33,486 volts.
Now that we have known the current flowing within the circuit, the output power of the line can now be easily calculated, since we are considering the total output of the line. 3 multiplied by the receiving end voltage, multiplied by the circuit current, multiplied by cos of the resistance all over 1000. This will equal to 52,000 kilowatts.
Likewise, the sending end power factor can also be calculated using these formula here. The ratio of the phase current to voltage of the receiving end voltage, plus the receiving end current all over the sending end voltage. This will equal to 0.80 degrees lag.
It is very important that we know these things, and be able to calculate them out. Because there is surely going to be voltage drop, and the drop varies according to the length of the transmission line before it will finally be terminated to the load. Hence the reason why the voltage is set up in such a way that the line loss will be negligible, thereby having little to no impact on the power received at the receiving end. And that is it for this triple series on the transmission line. In the next series, we will be looking at medium transmission lines. The way this line is analyzed using nominal T method will be looked at in detail. So until then, peace.